The James Webb Space Telescope, JWST, mankind's most recent enormous eye, connects across unfathomable distances, catching light that has ventured for more than 13 billion years. This light, anyway, recounts to us something other than an account of time. It uncovers the development of our universe, molded and extended by its continuous expansion. As we peer back at the most far-off systems, we're essentially seeing an old period moving increasingly close to the commencement of the universe, the huge explosion. The theory of prehistoric cosmic detonation, a basic story of present-day cosmology, strikingly suggests that our universe had a particular start and is limited in age. Yet, from its commencement, this solitary, grandiose beginning has been met with suspicion, and difficulties to its legitimacy endure, even in standard cosmology, for a really long time. The theory of prehistoric cosmic detonation held strong, particularly after the discovery of the infinite microwave background CMB during the 1960s. This background radiation, a weak, comprehensive murmur across the universe, adjusted flawlessly with predictions of a hot, thick early universe. Anyway, earth-shattering perceptions by the JWST lately feel a little unsure and raise new questions about the huge explosion's authenticity. Through the shocking lucidity of the JWST, NASA's grandiose time machine, we've seen groups of old worlds far bigger and more various than anticipated, testing how we might interpret the universe's earliest stages. As the telescope peers back to when the first systems formed, it offers humankind a remarkable view, one that the Hubble telescope couldn't completely access. Hubble was just not delicate enough to distinguish the very weak, red-shifted light of these earliest universes. Yet, with JWST's cutting-edge capabilities, we're looking as far as possible back, really close to time itself. And as we venture into this unknown region, we encounter a deep-rooted conundrum. How did the principal cosmic systems genuinely form? And does the universe, as far as we might be concerned, truly have a solitary, conclusive starting? The earliest universe was a hot, misty spot so thick that light itself couldn't unreservedly travel. This means that, regardless of how powerful our telescopes are, we can't notice any further back with light. Anyway, we are not restricted to light alone. New mechanical progressions are making the way for the detection of gravitational waves from impacting black holes, which could act as a new road to peer once more into the universe's earliest stages, maybe even into the very peculiarity we call the enormous detonation. The roots of the theory of prehistoric cosmic detonation and its growing distrust stretch back to the 1920s and 30s, when stargazers first saw that far-off worlds gave off an impression of being getting away from us. This discovery, combined with Albert Einstein's hypothesis of general relativity, set up the enormous detonation model. Einstein's conditions anticipated that a static universe would be unstable, requiring either contraction or expansion. Seeing this expansion proposed that worlds had probably been nearer together in the far-off past, suggesting a hazardous start for the universe. The universe's expansion has a few significant ramifications. Besides the fact that objects move farther apart, but the light emitted from them also stretches, moving to longer frequencies over time. Since frequency corresponds to energy, with more limited frequencies being more vivacious, this redshifting means the universe has been cooling as it ages. By rewinding this infinite expansion, we arrive at a point where everything would have been so hot and thick that neutral particles couldn't exist, leading to a uniform, burning hot shine. This shine was confirmed in 1964 when space expert Arno Penzias and Robert Wilson accidentally discovered the cosmic microwave background, an unavoidable radiation field faintly repeating the universe's red-hot beginning. Yet, as the JWST pushes the limits of enormous perception, researchers are finding features in the early universe that strain the conventional enormous detonation account. We see huge, glowing worlds where there should be none, bunching in manners that surprise everyone. So, if the theory of prehistoric cosmic detonation alone doesn't make sense of these oddities, what else could? At the core of the theory of how things came to be lies a peculiarity, a place of boundless thickness and temperature, where the laws of physics stall. This is where existence and time evidently begin. Yet this concept, while powerful, has limits. Imagine attempting to describe the sum of existence, compacting into a limitlessly thick point. This is where our understanding reaches a stopping point. Despite the fact that numerous parts of the huge explosion model have been upheld by perceptions and lab experiments, this underlying peculiarity remains a mystery, making one wonder, might the universe at any point have had an alternate kind of starting? In its journey to understand the universe, science has found ways to reproduce similar circumstances. Corkland plasma, for example, has been blended in labs, and matter-antimatter pairs have been created to line up with early universe predictions. Through these investigations, and by analyzing the vast microwave background's changes, we have an all-around supported image of the universe's advancement. Yet critical secrets remain. For instance, if all regions of space were once packed into a solitary point, why do we notice such uniformity in the universe's temperature? By conventional models, areas of space should show varied temperatures, since they could never have had the opportunity to exchange energy or information. Furthermore, we might expect to find remnants from the hottest epochs, such as magnetic monopoles or spatial inconsistencies, yet none are observed. These errors open the way for further possibilities. Either the universe intrinsically had these uniform properties all along, or there was some mechanism that imposed these conditions. One potential explanation is cosmic inflation, a rapid expansion conjectured to have happened before the huge explosion itself. On December 7, 1979, physicist Alan Guth proposed a revolutionary idea. He estimated that, before the hot, huge explosion, the universe encountered an extraordinary expansion. This inflationary stage could make sense of why the universe appears flat, homogeneous, and isotropic. After inflation, the universe would progress into the hot, dense state associated with the enormous detonation, making way for stars and planets to form. However, as researchers now acknowledge, even grandiose inflation from the universe's outset, proposing a sped-up formation rate that inflation alone doesn't explain. These observations have sparked excitement and reconsideration among researchers, as certain scholars are now forced to return to fundamental assumptions about how the universe formed. According to astrophysicist Erica Nelson, enormous universes observed within the first 500 million years of cosmic history defy existing models. The JWST's early findings suggest that systems from this epoch might be far larger and more varied than previously thought, possibly housing masses comparable to the present-day giants like the Milky Way. This rapid formation challenges current cosmological models, which suggested that such colossal systems wouldn't form until 1 to 2 billion years after the huge explosion. Nelson's research proposes that galaxies may be forming more aggressively than expected, leading to the potential for new theoretical frameworks for cosmic evolution. Dark matter, an invisible and mysterious substance thought to make up about 85% of the universe's mass, shapes the large-scale structure of the cosmos. Traditional cosmology suggests that galaxies form within massive halos of dark matter, which gravitationally attract ordinary matter, allowing stars and galaxies to coalesce. However, JWST observations challenge this model, as galaxies appear to be forming in ways that contradict our understanding of dark matter distribution. The presence of dark energy, a similarly elusive force responsible for the accelerated expansion of the universe, further complicates the picture. Some models suggest that early dark energy, a brief spike in dark energy density, might have accelerated the universe's growth in a manner that aligns with JWST findings. Yet, these variations must also reconcile with the broader framework of the standard cosmological model, which has successfully explained large-scale cosmic evolution. While the theory of prehistoric cosmic detonation remains compelling, it is not the only explanation for the universe's origins. Several alternative hypotheses continue to gain attention, each offering unique perspectives. The steady-state theory, for example, contrasts with the Big Bang, proposing a universe without a beginning, where matter constantly emerges as the universe expands. This theory suggests that, As galaxies move apart, new matter is produced, maintaining a consistent density. However, it fails to account for the CMB, which strongly supports a hot, dense early universe. Another speculative idea, the mirror universe hypothesis, posits that two universes were created in the Big Bang, one moving forward in time and the other in reverse. This twin universe would evolve backward, providing a mirror image of our own cosmic history. While highly speculative, it hints that the universe could be far more complex than we have imagined. The digital simulation hypothesis raises the possibility that our universe is a simulation created by an advanced civilization. Quantum entanglement and the strange nature of spacetime lend a theoretical weight to this idea. Although unprovable, the simulation theory remains an intriguing possibility in the search for answers about the nature of existence and the universe itself. As our understanding of the cosmos continues to evolve, tools like the JWST push the boundaries of knowledge, revealing new mysteries that challenge our deepest assumptions. Whether the universe's origins lie in a singular cosmic explosion, a continuous process of creation, or some other unforeseen mechanism, the quest for understanding is far from over. Each discovery, each anomaly, only deepens the questions and drives humanity forward in its pursuit of the ultimate truth about the cosmos.